In this lesson, we'll discuss hypothesis testing when you have two dependent populations. The question reads, a nutrition expert is examining a weight loss program to evaluate its effectiveness. 10 subjects are randomly selected for the investigation. The subjects' initial weights are recorded and they follow the program for 6 weeks, and then they're weighed again. The data are as follows. Take a look. Now we have to determine, does this data suggest that the weight loss program actually works? Let's begin by documenting the null and alternative hypothesis. We'll call this column 1 and this column 2. What we're hoping to see is that the averages of these is less than the average of this one, this group, right? Because in a weight loss program, the final weight should be less than the initial. What you want to see is usually the alternative hypothesis, whereas the null hypothesis is the opposite, and we denote that as H sub 0, where it's the opposite of this. It will be that this group is greater or equal to the averages of these. Now, to approach a situation where we have two dependent populations, we have to find the differences between each of the data here. For example, I have to subtract this number from that, and the same thing for all of these relative to those. So I will make a new column called D for differences and subtract them. 180 minus 165 is 15. 142 minus 138 is 4. And the rest of the numbers should look like this. It's important to note that the reason why we're finding the differences is because eventually we'll be using this formula to find the average of the differences. That number is then used to calculate the t-test. We also need the differences so that we can calculate the standard deviation eventually, where we need the difference raised to the power of 2. This means that I have to raise each of these numbers to the power of 2. 15 to the power of 2 is 225, 4 to the power of 2 is 16, and the rest of the numbers should look like this. Perfect. So let's take a look at these formulas again. If we want to calculate the average of the differences, denoted as d bar, we have to sum up all of these numbers in this column. And if we sum them up, you should get 66. Of course, you can use a calculator or do it by hand. You'll end up with 66 over, there are 10 subjects. Counted 1 through 10, and that's our n value. Dividing this out, it's 6.6. While we're at it, let's also calculate the standard deviation. Remember, just in case you forgot, that the variance is related to the standard deviation by being the standard deviation raised to the power of 2. So when I write down s to the power of 2, it's actually the variance. This means that after I find out what this side is, I have to square root both sides so that I eventually get the standard deviation. Alright, now that I've said that, let's go ahead and calculate the variance, represented as s to the power of 2. That's equal to the sum of all of these numbers. That represents this part right here. Let's find out the sum of all of those numbers. If you sum them all up, you should end up with 740. So the sum of all of these is 740, and that's that part right there. I'll write in 740 here, minus, we calculated that already, and it was 66, and it's being raised to the power of 2 over 10, and the denominator is 10 minus 1, that's 9. So let's use our calculator. 740 minus, at the top, 66 raised to the power of 2 divided by 10, and divide that by 9. We get this, and if we square root this, we get 5.815. I'll round that to two numbers after the decimal place, so 5.82. We got the standard deviation, we got d bar, now we can calculate the t-value using this formula. T is equal to 6.6, and for situations like these, UD represents mu1 minus mu2. So if we look at this formula right here, and I bring that over, I get 0 is less than mu1 minus mu2. And that is mu d. So we'll replace this with 0 because it's 0. Over, now the standard deviation, which we calculated, 5.82, over the square root of n. The square root of n is the square root of 10. In case you're curious, that's also the formula for the standard error. Let's calculate this quickly. 6.6 divided by 5.82, divide that by the square root of 10, and we get 3.586. 3.59. So this value right here represents t observed. And we'll be comparing this to the critical, which we'll use the table for. T observed is 3.59. The degrees of freedom is n minus 1, so 9. And we need to determine whether it's two tail, one tail, and if it's one tail, whether it's upper or lower. It's not going to be two tail because it's not equals or not equals 2. Instead, it will be one tail, and the significance level will be 0.05 because it's not stated in the question. We just assume that if it's not stated. And in our case, because mu1 is greater than mu2, according to the alternative hypothesis, this will be an upper tail test. Now we're ready to find out the t critical according to the t table. So the degrees of freedom is 9. It will be a one-tail test at 0.05 right here. We go down and it's 1.833. We have 3.59 comparing it to 1.83. As you can see, the t observed is greater than the t critical. And if we were to show this on a t distribution chart, when we found out what the t critical was at 1.83, and it's an upper tail, that's this region right here. So anything beyond this line would be rejected. 3.59 goes well beyond this rejection region. We've also learned that when t observed is greater than t critical, you reject the null hypothesis. So looking back at the null hypothesis, we have to reject the idea that the final weights are greater or equal to the initial. And what this means for us is that the diet actually worked. We reject the null hypothesis in favor of the alternative.